In this lecture, we will derive boundary conditions for magnetostatic fields. We have seen a general method for deriving boundary conditions for various fields, in which we saw that the integral equation for the divergence part, like in the electric field, we consider d dot ds is equal to rho free, and from that we could find that d1 minus d2n was equal to the surface charge density. Similarly, from the integral equation equivalent to the curl equation, we found that the tangential component of the field is equal to is equal in both the media. So we saw that this integral equation for the divergence equation gives us the boundary condition for the normal component, and the integral equation for the curl gives us the boundary condition for the tangential component. Now you should remember that since there is a discontinuity in the media, so we can see that the field may not be differentiable. So it is not mathematically accurate to derive boundary conditions from the differential equations, because at that boundary those are not defined. So we always derive boundary condition using the integral equations, and we assume that Maxwell's equations are valid in integral form on the boundary also. And so far, by experiments, it is seen that these equations are valid in integral form on the boundaries. So in this way, we should always remember that there is a very small difference in using differential form and the integral form of these equations, and whenever there is a boundary or discontinuity, we should always move on towards the integral form of those equations. So now let us try to derive the boundary condition for magnetostatic fields. So let us say that this is an interface. This is media 1, this is media 2. It is having mu1, mu2. So again, from medium 2, away from medium 2, this is the normal vector a and 2. And away from medium 1, this is normal vector a and 1. So we will first derive the boundary condition for the normal component of the field. So for that we will make a pillbox. So this is the pillbox, and this height delta h, we will in the limiting case take it to 0. So this is surface 1, this is surface 2. So for this bounding surface, this closed surface, for this surface, the normal vector for surface 1 is same as an1, and for this it is an2. Now let us say the magnetic field b1 is like this and b2 is like this. Now we will try to formulate the equation so that we can find the boundary condition using the integral equation b dot ds over the whole closed surface is equal to 0. So this surface is having three parts: the top surface, the bottom surface, and the curved surface is equal to 0. Now this curved surface, its area will go to 0 when we take this limit, that is we reduce this height to 0, so that we are just on the interface. So we need not worry about this. Now we just need to worry about these two. Now we are assuming that the surface is so small that b is not varying on this surface. Similarly, b is not varying on this surface. So at surface 1, this is surface 1, b is equal to b2 dot ds is equal to ds an1. And similarly here, For surface 2, B is equal to B1 and ds is equal to an2 is equal to 0. Now since I have assumed that these surfaces are very small, so I can take out B2 outside, B2, and this is now you can see that an2 and an1 are kind of opposite in direction, so I can write an1 is equal to minus of an2. So I will put this ds an2 with a minus sign plus over surface 1. Similarly, b1 dot ds an2 is equal to 0. So b2 dot delta s, let us say this area is delta s. Similarly, this area will be delta s. An2 with a minus sign plus b1 dot delta s an1 is equal to 0. It implies b1 minus b2 dot delta s, this is an2 is equal to 0. Since delta s is not equal to 0, it implies that b1 minus b2 dot an2 is equal to 0. So in this way we have derived the boundary condition for the normal component. Since b1 dot an2 is going to give us the normal component for the field, so b1n minus b2n is equal to 0. So that is b2n dot an2 is also going to give us b2n. So I have put these two in this equation and I have got b1n minus b2n is equal to 0, or it implies that the normal component of the magnetic field is equal in both of the media. That is, it does not suffer any discontinuity on the interface. So this is one of the important boundary conditions for magnetostatics, because we can utilize this because we know that the magnetic field, its normal component is not going to suffer any discontinuity. Now we want to derive the boundary condition for the tangential component. Now that is little lengthy. We should properly see and we should try to understand how to derive that. Now, as I have told that to derive the boundary conditions for tangential component, we need the integral equations for that curl law. So we know that h dot dl over a curve which is enclosing a surface is given by j dot ds over that surface. So if let us say this is 1, this is medium 2, and I am assuming that I am taking a curve in this direction like this. So this is curve C which is enclosing this surface area. Okay, so this surface area is delta S. Now the current through this surface area is equal to this integral along this boundary, or the line integral over this boundary. Now since we want to derive the equation in vector form, so we will introduce, for the sake of ease or simplicity, I will just assume that we have x-axis in this direction, y-axis perpendicular to this, and z-axis perpendicular to the paper. So this is x-axis, this is y-axis, this is z-axis. So let us say this is delta x, this is delta y. Okay, so Let us solve this part first. So here let us say h1 is there and here h2 is there. So for this part, h1 dot delta x ax will be there for this part. Now we need not worry about this part because ultimately this delta y in the limiting case we are going to take it to 0 because we want to find at the interface. So I am not going to write these two. So I will just write now this part. So this is h2 dot delta x, but its direction is in opposite to the x-axis minus ax. Now this is the left hand side, or I can write it as h1 minus h2 dot ax delta x. So this is the left hand side. Now we need to find the right hand side. Now this whole surface delta s is equal to, this area is equal to delta x delta y, and its direction will be in az direction. So this right hand side will be equal to the current density. Now since I am taking that this delta is very small, so I am assuming that the current density is not going to vary, so it is easier to take it outside the integral. So j dot delta x delta y az. So let us continue on the next slide. So h1 minus h2 dot ax delta x is equal to j. Now we know that delta y is going to 0 in the limiting case. So I will subsume or include this delta y with the current density jy dot delta x az. Now the reason to do this is because we are assuming that this volume current density is such that even if this delta y tends to 0, the resultant is not going to be 0. It implies that the volume current density is kind of singular in nature, so that this multiplication is not is not 0, that is it is non-zero. So this thing will be called as surface current density, means the current will be flowing and its thickness, this width will be very small. The current will be flowing like this and its thickness will be very small, that is this thickness will be tending to 0, but still there will be current on the surface. Okay, now this case is possible only if we have perfect conductor. Only in perfect conductor current can just flow on the skin, the top skin. Otherwise if there is a normal conductor, current will have to flow in a little non-zero thickness, that is thickness will not be 0, so there will always be a volume current density instead of surface current density. So you should always remember that this surface current density can only occur in perfect conductors. So this js will be there, delta x az. Now we need to somehow uh, bring az in this side also. Delta x will get cancelled out, so we have h1 minus h2 dot ax. Now we have to somehow bring az so that we can equate both of sides. Now ax is equal to ay cross az. So I can write here h1 minus h2 dot ay cross az is equal to js dot az. Now you see this is x, this is y, and this is z, or sorry, z is actually, this is z. I think labeled it incorrectly. So this is x, this is y, and this is z. So please remember that this right hand rule should always be followed by the coordinate system. So this is x axis. I have just labeled it incorrectly, otherwise I have taken everything correctly. So while writing you should remember this is x, this is y, and z is outside the paper. So all those things are correct, only this labeling was incorrect. So now you see this Az is in this direction, that is perpendicular to the surface. Okay, so I can write actually Az as an for our surface, but we will do it little bit later, so that first we can resolve this. Now you know that I can write it as A dot B cross C. Now you know that it is equal to B dot C cross A, and it is also equal to C dot A cross B. So both of these are equal. So what I'm trying to do, I'm trying to get dot product here on both sides with Az. So how is it possible? This Az comes into the dot product, that is this form. So this I will write now Az dot, now A cross B, H1 minus H2 cross B, B is AY, is equal to JS dot Az. So you see, now this is a unit vector, and the vector which is having same component along that thing, we can equate them now in the limiting case. So H1 minus H2 cross AY is equal to JS. Now let us see what is AY. This was the interface, this was 1, this is 2, and y was in this direction. So this was AY. Now you see, according to our terminology which we have just seen for the normal component, this is nothing but equal to an1, the normal vector from 1 to 2. So I can change AY to an1. So H1 minus H2 cross an1 is equal to JS. Now since in our the normal component, we have written b1 minus b2 dot an2 is equal to 0. Since we have utilized an2, so to bring uniformity, now we want to convert it to an2. Now we know that an2 is equal to minus of an1. So I will write it as h1 minus h2 cross minus of an2 is equal to JS. Now this minus of an2 can be, now because this is a cross product, this minus sign can be taken inside if I reverse the this these two with respect to the cross product. So I will write it as an2 cross h1 minus h2 is equal to JS, wherein I utilize that A cross B is equal to minus of B cross A. So this is what we have utilized. So this is the boundary condition for the tangential component. Means now you can see H1 cross an2. If this is medium 1, this is H1, and an2 was like this. So H1 cross an2 is going to give us only the tangential component of this H1 cross an2. So this is going to give us only the tangential component of this field. So this is normal component. If let us say the field is like this along the interface, this is the normal component, this is the tangential component. Now you see, tangential component can be thought of in any way. That is, if this is the surface and this is the normal downside, now the tangential component can be this, can be this, can be this along the surface in any direction. So you see, the tangential component is along the surface. You just remember this, in any direction. It can be in this direction, this direction, this direction, but it is always now along the surface. Okay, so now in this way I can write this as h1t minus h2t is equal to JS in the scalar component form. It implies that the tangential component of the magnetic field intensity is discontinuous if and only if there is a surface current density, and this surface current density can only occur only if we have a perfect conductor. So for normal practical cases, this is always going to be 0, because this volume current density cannot be a singular quantity to give us a non-singular or non-zero surface current density. So in this way we have derived both of the boundary conditions, that is B1n is equal to B2n, H1t minus H2t is equal to Js. I have also derived them in the vector form, B1 minus B2 dot AN2 is equal to 0 and H1 minus H2 AN2 cross is equal to Js. So these are the boundary conditions which we should remember, and we should compare them with the electrostatics case, in which we had AN2 dot D1 minus D2 is equal to rho s, and AN2 means the tangential component, that is E1t minus E2t was equal to 0. Means we could have written AN2 cross E1 minus E2 is equal to 0. So the things are quite similar in both magnetostatics as well as electrostatics. Only the difference is that here the normal component is continuous, here tangential component is continuous, and here the source is surface currents, and here the source is, or this discontinuity is surface charge density. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel and join us in our Telegram group, whose link is given in the description of this video. Thank you.